Okay, so I want to discuss why we can in finitely many steps find a. So what we had is we had p was irrational, q was not irrational, and we had another number up here which was a. And what we wanted to prove is that within finitely many of these taking averages, we can get a rational number that's within here. And to get a rational number within here, we have to get a to a point where, so let's call the distance between here epsilon, and let's call the distance between these two, we'll call that a to the n. A to the n. So it starts off as a to the 0, but after taking n number of averages, it's reached a new value. So a1 is the value that it's reached once we've taken a new average, we've moved a slightly closer, the picture's not to scale, a could be right off over here somewhere, and we've got a new distance, so a1 and then a2, a3, etc. So, okay, so what we need is we need an within finitely many steps, so for a finite n to be less than epsilon, because if it's less than epsilon, when we take the average, we'll get a rational within here, won't we? Okay, so let's try and prove that eventually it will get to that. So what do we know? We know that an plus 1 is going to be equal to, what do we know? Think. What are we doing each time? We are so when we average them, we are dividing this, we're taking the distance an plus epsilon, and we're dividing it by 2, and that's going to be the overall distance from here, so the distance along here. So we then need to subtract epsilon off from that, don't we? Which will give us the distance from q, because the distance an is the distance from q to a at that point. Oh, this stupid camera, what is it doing? Right, so, terrible piece of kit. Right, okay, so this is the distance from Q to our point A after no, this is the distance an plus 1, so it's the distance n plus 1. You take the distance as it currently is, you add epsilon over 2 and you subtract epsilon, so it's overall an minus epsilon over 2. So we've overall got a recurrence relation, an plus 1. So I'm going to write it as a difference equation. So minus an is equal to, subtract minus an from both sides, and we get negative an over 2 minus epsilon over 2. Now, once you've solved enough of these difference equations, you can recognise what this is going to be. It's going to be an exponential of some sort. So we're going to get that an is some constant times an exponential. This isn't necessarily e. This isn't necessarily 2.71. It's just going to represent some exponential, some base that we haven't yet worked out, to the power of x plus some constant b. Okay, so what we need to work out is how to. Oh, what have I done? It should be to the power of n. Okay, so what we need to work out is what is this term here. So we need to work out what is an plus 1 minus an. So it's going to be ce to the n plus 1 plus b minus ce to the n plus b. Okay, and that's in brackets. So that's going to give us e to the n plus 1 minus e to the n. We can factor out an e to the n and we'll get e minus 1. And the b's will cancel. So here we have our expression, right? So here's the clever part. Ce to the n was equal to a to the n, wasn't it? Ce to the n plus b was equal to an. So ce to the n is an minus b, isn't it? So it's equal to an e minus 1 minus b e minus 1. And now we look back up to up here and we compare coefficients. So we've got a constant term here which compares to this, and we've got this term here which compares to this. So e minus 1 needs to equal negative a half, so e is equal to a half. So e minus 1 is equal to negative a half, so we stick that in here, and we get b over 2 must equal negative epsilon over 2. So b is equal to negative epsilon. Okay, and the arbitrary constant is just something that we're going to decide from our initial condition, the fact that a0 is equal to a0. So that gives us, that's our initial distance of a from q. So we're going to work that out in a moment. So stick these in and we get an is equal to c, a half to the power of n, but that's the same as 2 to the negative n, plus b minus epsilon. Okay, there you go. So now now what we know is that when n is equal to 0, a is equal to a0. Yes, a is equal to a0. The distance between them is equal to the initial distance. Okay, so n is equal to 0, this goes to 1, so c must equal a0 plus epsilon. Correct, is that correct? So n is equal to 0, that gives that to 1. An is equal to a0. Yep. So we get our final expression that an is equal to a0 plus epsilon, 2 to the negative n minus epsilon. Okay, so now what we want is we want that to be less than epsilon. Okay, so a0 plus epsilon, 2 to the negative n is less than 2 epsilon. 2 to the negative n is less than 2 epsilon over a0 plus epsilon. N, remember, has to be an element of the integers, a positive integer. Or 0, it can be 0. But so this is 1 over 2 to the power of n. Everything here is always going to be positive, isn't it? Yes. So I don't think there's any issue with doing this. So we can flip them to the other side, plus epsilon over 2 epsilon. Oh wait, yes, is less than 2 to the n. And then n is thus given by log to base, well, not is given by, n is greater than log to base 2 of a0 plus epsilon over 2 epsilon. So basically, you give me an initial value, or, oh, sorry, you can't see this. Basically, you give me an initial value for your distance of the point A from the point Q. You give me an initial distance between P and Q, and I can work out this logarithm. You just stick those numbers in and work out this logarithm, and basically just pick the smallest integer, but you don't necessarily have to pick the smallest integer. You could pick whatever integer you... well, actually... yes, you can pick whatever integer you want as long as it's greater than that, and do it that many times, and you will have gotten your correct... you will have gotten a rational number in between the P and Q.